Hello, everybody. Good morning. Right, so the topic today will be on satisficing, or what Herman Simon termed later in his career the best so far. So what exactly is satisficing? I'll try to give you some insights and a good gut feeling, basically, during this talk. Satisficing often is contrasted with optimization. Optimization is in a situation where you have ex ante, so before you make the decision, sufficient information really kind of to apply some optimization calculus to determine the best course of action. Now, however, often you might not be in a situation where you really do have such information, basically, that you can be sure that you can apply optimization. For instance, in the context of learning, where you have to acquire information, optimization might or might not work very well. Similarly, in a dynamic context, basically, where the information today might not be relevant tomorrow anymore, you might be in a situation where optimization might not work very well. And what I'd like to illustrate first, basically, in the first large study, is how frequent is it really that satisficing and optimization kind of perform well? So when does one of the two really outperform the other? And secondly, the question is, why might satisficing outperform optimization? Right. Now, the second study then, so we will have initial Q&A session after the first study in order really for you kind of to get a better understanding and focus on the first study. Secondly, I'd like to introduce you to a study where we're looking at the aggregate level, actually it's a market basically, and the individual level, individual decision makers, the dealers here, in that case, firms, and show that depending on your level of analysis, you can take on very fundamentally different perspectives on how to make decisions, basically. On the aggregate level, optimization might work very well, actually. At the individual level, it might not work at all, but a rather satisficing mechanism is employed really to make successful decisions. Right. So just briefly, to kind of give you the kind of core bullet points, we're looking at optimization and satisficing. And optimization, you need to have sufficient information on all alternatives, outcomes, and probabilities, the kind of decision making and the risk, as Knight termed it, basically. Now, you have to have a sufficiently stable environment, and also needs to be sufficiently simple. If all these three conditions are given, you can be pretty sure that optimization is a good road, basically, and will lead you really kind of to the best choice. However, if any of these three things are missing, so you have limited information, well, not quite surely what to do. A dynamic environment, or it's complex, satisficing or optimization might be working. So satisficing should be rather here with a question mark, but it certainly must be tested, and it must not be taken for granted that optimization is the best course of action necessarily. So as I said, study one focuses on how frequently is it really the case that satisficing can outperform optimization calculus of different sorts in the first place. Secondly, why might this be the case? Right. So with this study, actually, we go initially back to 1912 in London. In London in 1912, a catalog company was operating. And what they basically did as a business, they were sending out big catalogs of clothes to the customers, and customers would be able to select the clothes from the catalogs and order with that company. Now, a big problem for that company was that sending out these catalogs obviously was very expensive. So sending out to a customer who would not buy with them anymore is just kind of money wasted, essentially. So they had a prediction task in that case, predicting which customer is likely to buy with them, right? And in the end of the day, actually, they zoomed in on a very simple strategy, a heuristic, which later has been termed the hiatus heuristic. They simply kind of used a fixed threshold, say 6 months. And if a customer bought within these 6 months, the customer was predicted to buy again. Whereas if the customer did not buy, the customer was predicted not to buy again, basically. Now, the question is obviously kind of given such a kind of simple strategy that only relies on recency, that is, how long ago a customer bought with the company, how well can the strategy perform in the first place. Secondly, an important point here is the basic scenario doesn't only apply to companies, but it applies actually to many other scenarios where you have to predict whether an event will occur or will not occur anymore in the future. That is, if you're at a hospital, for instance, you might be interested whether a patient will be readmitted to a hospital when he has been treated in the first place. Or you might be looking at, for instance, tornadoes, if you're, for instance, looking into buying an insurance against tornado damages. whether or not kind of to buy that insurance depends on your assessment of whether or not the tornado might occur again, basically, right? And now what all these examples have in common is obviously is they zoom in on recency. So how long ago has an event occurred? Has a customer bought or a patient been admitted, or a tornado actually struck a certain city or location, essentially. However, obviously, there are many, many more informations out there. It's not just recency, but also frequency, how often a customer bought, how often tornadoes strike a certain location, or the severity also, or the damages that a tornado causes, how many people are involved in damages, etc. Right? So potentially you have many, many different informations basically in these scenarios, and what we kind of test here is a simple hiatus heuristic against different strategies that use all information and try kind of to calculate an optimal probability with which event occurs, and therefore kind of allows to predict the future. So what we have here as an abstract view, so on the one hand, we have a calibration data set where you have an observation of event E, so whether or not a customer bought, basically. These 3 dots are, or 4 dots are observations when actually customers bought, for instance. And then you have to predict for the holdout that is not contained in the original data set where you actually fit the models. Basically, you have to predict whether or not the event reoccurs again. As I said, there are at least 2 leading explanations. One is recency, and people have been often observed to rely on recency only. Actually, it has been dubbed as the recency bias, so a pretty bad idea to rely on recency only. But one often uses, for instance, in statistics, also frequency, like a frequency count, basically, actually should be kind of the most important variable that informs your decisions. And as I just explained, there are many other variables, basically, that can be taken into account. The hiatus heuristic only uses recency, so it takes a fixed threshold and observes whether a customer or a tornado or whatever kind of occurred within the last, say, 6 months or so. If it did occur, it predicts it will occur again. And then we compare this heuristic against 4 more complex models. On the one hand, actually models from marketing that specifically focus on predicting whether or not customers will buy again. So these are stochastic models, Pareto NVD and BG NVD. Secondly, we used from machine learning, state-of-the-art model, a random forest, basically, where we fed all the information in, which also made then the predictions. And lastly, we used something that is kind of more common, I guess, kind of especially among practitioners, a conventional logistic regression, so just a linear model, essentially. And then we tested how often one of the 4 models basically performs best, and when and why. Yeah?
Why do you call it the calibration? Has anything to do with the theory?
Well, calibration is basically, so you take a data set, say 12 months, and you focus only in the first 6 months. You actually estimate the parameters of your model. There, for instance, in a logistic regression, there would be kind of the beta weights, essentially. And then you make the prediction on a holdout data set that has not been seen beforehand, basically. So this is really kind of, you are here today and have to predict tomorrow, and you don't know what's will happening tomorrow. If you do some sort of cross-validation that is similar but not quite the same, really, because in a cross-validation where you have different folds in the data sets, for instance, that these folds imply that to some extent the data actually integrates also what we'll be looking in the future. And this is really a radical approach, kind of in terms of out-of-sample testing. Yeah, which is important because obviously today we don't know what will be happening tomorrow. Yeah.
Sorry, if I may, how is this threshold estimated?
Right, that will be happening in a second. It's an important question. Now the issue here is optimization versus satisficing is in terms of an ecological rationality, right? So when can it be that satisficing really outperforms optimization? So we have 2 core hypotheses here. On the one hand, it's estimation, so it's simply difficult to reliably estimate the parameters. This might be specifically due to a limited sample size. So the smaller the sample you have, basically, if you only have 2 data points, you fit a complex, you estimate a complex model, basically, obviously this complex model can't do very well. But the larger the data, in an age of big data, basically, estimation should not be a problem at all. Therefore, all complex models should perform well given kind of large data sets. Now, the second hypothesis that we have here, it's not that it's so much due to an estimation error, but that recency in and of itself is such a strong variable that you don't need any other information to make a good prediction, basically. Adding other information, any other variables to recency, just kind of makes the same prediction, or potentially leads to overfitting, actually. That is actually a worse decision in the first place, right? That's what we mean by non-compensatoriness, that recency by itself cannot be affected by any other variables in the first place in terms of its predictive performance. Now, what we have here, we altogether have 60 data sets, as I was trying to allude already at the beginning, really kind of looking across a wide range of different domains. On the one hand, we have classic retail, and really kind of to look at what did these marketing managers do in 1912? Is this still applicable today? Because many companies today still use the simple hiatus heuristic. And then also really applying kind of a specifically developed algorithm, that is the Pareto NBD and the GNBD model, to these data sets and test whether kind of these specific algorithms perform specifically well in these environments. And then we have 36 non-retail environments. This is health, so we talked about the hospitals. This is sports, so predicting whether or not a team will win again, for instance, will win another championship again in the coming year. We have accidents in here. This includes actually terrorist attacks, so whether a city or a country will be struck by another terrorist attack, actually. But it also includes car accidents, whether the specific road, basically, another car accident will happen. We have weather here. This is the example with the tornadoes, banking, whether somebody will withdraw money, and a number of other data sets, which includes, for instance, whether or not you will be accepted at a highly competitive conference. Yeah. And across all these 60 data sets, basically, we evaluate which of these strategies really performs well and which doesn't. And just kind of looking at the raw statistics here, giving you an overview. So what is important here really kind of is the minimum maximum here. So in terms of sample size, we have really very small samples going up to rather kind of large samples, basically, think of in customers, so 16,000 customers or 18 customers. This is rather actually the tornado scenario. Number of time units that we're observing. So time units might be days, weeks, or months, basically, going all the way from 6 months, actually, up to 156 weeks. Share of reoccurring events, so that is how difficult it is. If we have a very low or very high number of reoccurring events, it's more easy, basically, in comparison to somewhere in the middle. And the number of variables goes from 3 up to 10, basically, right? So there's a fair amount of heterogeneity in this data set in order to really assess, basically, when is satisficing a good idea and when is it best kind of to really optimize. When is recency maybe kind of a good strategy in the first place. Now, we already had the question, basically, how do we estimate the threshold of the hiatus heuristic? Because the hiatus heuristic, also there you actually can apply optimization, right? So kind of determine the optimal threshold. So just kind of take again the example of the 12 months. You just have initially 6 months where you obtain data. You might be able to determine the optimal threshold in your calibration data set, or you might simply take some kind of robust statistics like the median of the period, right? So kind of say like 3 months is kind of the cutoff, my threshold, and then I compare that kind of to an optimization procedure. Now, one really would expect, basically, across these 60 data sets that very, very often my optimization procedure should be yielding determining the optimal threshold should be really yielding kind of the best performance in comparison to kind of simply taking kind of like a 3 months cutoff the median year, right? Now, what we present here is exactly across those 60 data sets, how often Satisficing outperformed the optimal threshold for the hiatus heuristic. So that is across all the models that we have, and I'll be explaining in detail kind of what these models exactly mean. So we've got 60 cases, 60 data sets. For the hiatus heuristic itself, in 44 out of 60 data sets, it's best just kind of to take the median as opposed to try to estimate an optimal threshold. Right? So 44 out of 60 cases, the Satisficing outperforms our optimization. And with regards to these other models, so random forests here makes a probabilistic assessment. So it tells you with a certain probability if an event occurs. And also here you need a threshold. So you can determine the optimal threshold here also. So which might be, I don't know, like 60%, whatever, in terms of dividing whether or not an event will be reoccur. Or you can simply also take here the median of 50%. right? And also here you observe that actually, if you do not optimize, but rather kind of take the median, in many of these environments, you actually observe that this kind of satisficing algorithm, so to say, actually outperforms optimization. Specifically here, we have random forest with only recency as a variable. It's in 48 cases, 48 data sets the case that satisficing outperforms optimization. If you include all variables that we have, so up to 10, it's still 38. And if you take recency out, it's still 35, basically. We have the same pattern, basically, for logistic regression. Just here, it's much more stable, actually. So between 47 and 45 data sets out of 60, it's actually best to use the satisficing threshold. And for Pareto NBD and BNBD, the numbers are a little lower. But in more than half of all data sets, we can say, basically, satisficing outperforms optimization. Yeah. Now, what we are also particularly interested in is how often, kind of the predictive performance, basically, across all these algorithms. So how often, really, the customers is predicted correctly as being active or inactive, or the tornadoes is predicted correctly as occurring or not occurring, basically, right? So what we have here, again, is a comparison in terms of accuracy. And these all take the satisficing threshold, because this is very often kind of the threshold that actually yields the higher performance. Very similar results, but just kind of with lower accuracy is obtained when you actually look at the optimization threshold here. Hiatus heuristic performs best, basically, across all these 60 environments and achieves an average performance of 71%, basically. So just one variable, this is recency. In this simple heuristic, where you just have a satisficing threshold, is actually able to outperform, on average, that is, across these 60 data sets, these much more complex algorithms. So here we've got random forest. And what is also really interesting is that the performance, when you only plug recency into random forest, so a very, very simple model, is the same as if you actually have all data insert, or if you actually exclude recency. So statistically, this is not different. So you might very often just rely on recency, and the kind of the small difference here might be due to actually overfitting, even with one variable only of the complex model. Yeah.
Just a clarification question. So if you do it on all data, like random forest or logistic regression, it's not optimization.
Say again?
So how do you define optimization here then?
So optimization, first of all, is with regards to the threshold, basically, which I just showed you, right? And then the next procedure, obviously, is once kind of you have determined where your threshold is, random forest then applies an optimization algorithm in order to kind of determine the optimal tree, essentially. That's what I mean by optimization in that regard. Also, logistic regression, obviously, kind of the beta weights are determined in an optimal fashion.
So the all data bars will be optimization, and the recency ones would call satisfying.
No. So here, basically, kind of you determine exactly kind of where the divide is, essentially. No, actually, you're right. Exactly recency here. Exactly no. Exactly recency here. That's actually you're right. Yeah, like a satisficing algorithm. That is optimization as well here. And here, because you've got an intercept as well as the beta, that's optimization. Very good observation, actually. Yeah. Right. Now, the question obviously is, why is this the case that such a simple heuristic or satisficing can yield such strong results? So is it something kind of peculiar in the data sets? And a first observation that you might take here is simply kind of the retail versus non-retail environment, specifically given that we have Pareto NBD and BNBD in there, which are specifically developed in marketing to make these predictions. Is it that these models perform suddenly much better? And no. The same pattern in terms of performance can be observed, whether it's retail or non-retail, in terms of I get patterns across all these 60 data sets. So this is not the case. This must be something different. However, if you look really kind of in detail across these 60 data sets, so we've got here all 60 data sets. Here again, the performance. Red is the hiatus heuristic, blue the random forest, green the logistic regression, and black Pareto BNBD. There is a considerable heterogeneity. suggesting, okay, we really must understand the specific environment when and what type of algorithm performs well. So in the first environment, it is indeed a logistic regression that by far outperforms the hiatus heuristic, whereas there's still a number of environments, obviously, where the hiatus really outperforms all other algorithms. And there's even some environments, such as here, where Pareto BNBD performs best, right? So just kind of saying, okay, I know now I must kind of use a heuristic. This is not the correct answer, but rather kind of really understand the specific environmental context in which you're operating. Now, before we go to more detailed analysis, what is really interesting here is to initially observe which is kind of the most powerful variable in general. And what we have here is from the random forest, you can deduce a variable importance rank, so which variable is the most important in order to make good predictions. And across these 60 data sets, you see that recency here, which is at the core of the hiatus heuristic, is the most important variable in 39 out of 60 data sets. And in about 15, it's the second most important variable. And compare that to frequency, right? Which often is assumed kind of to be kind of a very core variable when kind of doing any statistics. And frequency is the second most important variable in all data sets, but only achieves a much lower variable importance overall. So this suggests that recency really is kind of, if you identify a central driving variable in a given data set, this is very often possibly sufficient to obtain good performance. And you don't even need to go into frequency, basically. This is what it suggests. And that's more specifically, basically, what I've been just alluding to. So this specifically tests in a regression our two core hypotheses that satisficing might be a good idea given a limited sample size, so up here, or that satisficing might be a good idea given a non-compensatory environment, so where recency really kind of is the most important variable and cannot be outperformed by any other variable. So what we do here is we have a regression where we take the performance difference between the hiatus heuristic and the random forest, basically. So that's the random forest gap, respectively the performance difference between the hiatus heuristic and the logistic regression, respectively for PNBD, so Pareto NBD, and then kind of regress all of these independent variables. And what you see here, in terms of the performance of the hiatus heuristic, is that sample size does not affect its performance. So it's not that given a small data environment, this is precisely where I should be using a heuristic that relies on recency, a strategy that only relies on recency, and a heuristic strategy on top of that. But it's rather kind of that it's non-compensatoriness, so the importance of this variable, which is key in driving these results. So even if you have many data, basically suggests you still often can rely on, should rely on recency and can ignore the rest of the world, basically.
So clearly, recency is correlated with frequency. The more frequent an event is, the more likely it is to occur.
Exactly.
So have you examined the impact of recency once you remove the impact of frequency onto recency? And see if it's actually truly recency itself that's important or somehow influenced by frequency?
Right. No, I mean, there's a high correlation between recency and frequency. And generally, there's a high correlation between recency and a number of other variables. And that kind of makes part of the explanatory power of recency, because it kind of sucks out much of the explanation that other variables can provide in the first place, and particularly recency. But, I mean, there are other variables, basically, that you can construct in terms of like a time series, and they just don't provide any additional insights in many of the data sets.
So is there generally a strong correlation between the degree of non-compensatoriness in the variables and how well the heuristics performs in the data set?
Right, so that's not a matter only of correlation, but it's actually given a certain environment, so without uncertainty, so where you don't have any estimation error, basically. Given that recency has such a high weight, basically, you can ignore all other variables, right? So it's not just a correlation, but that can be derived by a proof, essentially.
I guess what I'm trying to say is, if you encounter a new data set that you have never encountered before,
yeah,
would it be a good procedure to just look at, using random forest or whatever, which, if there is no compensatoriness in the variables, and then say, okay, well, I should use a heuristic because clearly one variable is much stronger than the others, I shouldn't really bother about anything else. Would that be a fair?
Exactly, yes, exactly. That would be a fair assessment, basically. If you can be sufficiently certain that the variable is non-compensatory, then exactly nothing else can be done, basically. The performance of adding other variables can be only as good as, or in the worst case, can be worse because of overfitting.
Right, which means that if I encounter a data set where there is no clear evidence for that,
yeah.
then is it fair to say I should maybe not try heuristics? Because I am fairly sure they're not going to work compared to the others?
Right, exactly. Then you should kind of try alternative mechanisms, basically, but certainly not kind of just rely on this one variable. Yeah. Okay.
Right. Two questions. Can you explain how you measure non-compensatoriness?
Right. So yes, that's a very good question. So that's kind of also why we have these three different algorithms in there. So non-compensatoriness in this case is measured via the logistic regression. So it's really kind of estimating the beta weight, basically. And given that the weight of recency is larger than the sum of all other weights, the results of recency cannot be kind of turned in the logistic regression, right? And that's basically, we have then like an indices for each data set, whether this non-compensatoriness is the case, and that's what you precisely see up here.
So the weight of the coefficient.
Yes, the weight of the coefficient
is more than the sum of all the others.
Exactly. So it's really kind of looking at the environmental.
That's sort of an approximate coefficient, right? So still, it could be something soft out of it, as you said, but not a lot.
Say again?
I just have to think a bit more about it. What is clumpiness?
Clumpiness is basically how evenly distributed the events are. So you might think kind of like sometimes events kind of occur clustered together, right? And sometimes kind of they occur kind of in very regular time intervals.
Again, as a variable, how do you measure that?
Well, you kind of take the distance between the events basically, and look at how similar kind of the distance between the events essentially is. That's kind of what the metric basically does. No, it's not that objective, but kind of we're looking at the data. So clumpiness is like in machine learning, kind of a conventional a measurement essentially of kind of the regularity in the data set. Yeah. And I mean, what you can see here is basically is that the more clumpy is, the more irregular data set, kind of the better the heuristic. The more clumpy, obviously, kind of the worse, kind of the more complex algorithms do, because it's a more kind of complex, more difficult environment. Yeah.
My question was on the different kinds of data sets. So some of them look like quite zero inflated, like terrorist attacks. And then you already know that the logistic regression is quite bad. Then you need something like sparse covariance matrices, so like to penalize for that.
Right.
Is there like, do you also see that in here then? That
right.
The type of events, you see then very simple algorithms are much better than this standard logistic regression, for example.
Right. I mean, I guess kind of that's kind of a little bit the problem kind of dealing with so many data sets, right? Kind of so you kind of can zoom in particular kind of aspects of a given data set, like the terrorist attack data sets, or you can really kind of try kind of to find more aggregate patterns.
But zero inflation is a very simple measure, for example. So.
Okay. We haven't had a look at it so far, but maybe then that we should consider that also. Okay. Yeah?
So the fact that random forest also performs badly is a bit more convincing to me, but also then some of the data sets are known to be problematic to predict.
Right. I mean, generally kind of there's a different, I mean, there's a variation in terms of difficulty to predict basically in the first place. That's kind of where we have kind of the reoccurring share here and there, basically. That's kind of an indication of the difficulty of a data set, right? And obviously kind of, especially for logistic regression, basically kind of it has a strong explanatory power. Yeah.
So the techniques that I see here, they're generally not, we're not conceived for like time series, right? You can adapt that to some time series.
Exactly.
So, do you have any intuition on what would happen if you use something like simple as like a moving average or something like that?
Right. So we also have tried a number of time series analysis, and in the end, they kind of be stuck with those kind of three algorithms, because Pareto NBD is kind of that's the kind of the state of the art really in the marketing literature, and the other ones are kind of help us kind of to analyze the data set basically. But when we kind of did look at time series analyses basically, they also didn't perform much better in the first place. So they also had difficulties in estimating the relevant parameters essentially. And also they're kind of the more simple basically, very often the better actually their predictive power. But yet again kind of a more a better statement with regards to when and where you would be actually using time series analysis would be something, a totally different study, I think, than what we did here. Yeah. Okay. Then let me quickly move on. So obviously kind of what is important here also is that it might be kind of regarded as pretty arbitrary kind of to divide the data sets like in terms of two. So kind of having 12 months, 6 months calibration and 6 months holdout where you have to predict basically. So the question is if you have a different split, so say 3 months for calibration and 9 months for prediction, how does this really affect kind of the performance of the variables? Now what we did here, again, we kind of have the three basic models and then size of the calibration sample. So here it's only 25%, 50 and 75% of the sample basically. And then we also have in terms of holdout, so how many units ahead you're actually predicting, 1 time unit ahead or 5 time units ahead. And what you generally can see here is actually, so if you only rely on recency and the hiatus heuristic, if you have only 25% of the sample available, then this is actually too little of a history in order kind of to really make good predictions basically, right? Because very often you do not have a sufficiently long time period where you kind of can capture recency sufficiently well essentially, right? But recency actually does need a sufficiently long time horizon in order kind of to really kind of capture recency sufficiently well. And then kind of given this kind of time horizon as a 50% or 75% basically of the sample that we have, then it performs on par or outperforms basically with the more complex methods. Yeah. So just a summary quickly of the first study here. So what we have seen here, recency dominates many environments. Other variables often can be safely ignored. And that is satisficing in this case can be a very good idea. That is not only just for the hardest heuristic, but also for the more complex algorithms. The good performance basically of the heuristic is not due to sample size, but it's really due to the importance of the variable. So recency in itself is so powerful that you often can ignore other variables. And what we've seen at this last slide basically, still for recency, you do actually need a sufficient history. You can't simply kind of just look at yesterday and then kind of assume since yesterday the event didn't occur that it also will not occur in the future, but that you actually need to have a sufficiently long time period. Right. So what I also like to ask you now is kind of to quickly dive into this study, ask some questions before then we moving on to the second study, because this is somewhat different. So what I said kind of before, that another important distinction isn't just kind of the variable importance, so kind of just as recency, but also kind of the level of analysis that you're taking on. So whether you're at the individual level or at the aggregate level. And at the aggregate level, particularly kind of market play an important role. Economists kind of do very often kind of aggregate market analysis. That's kind of where the homo economicus, the rational agent has been developed also basically. But at the individual level, something totally different might happen. So firms might act totally different than kind of actually assumed at the very aggregate level. And this is actually well, because of the uncertainty present. And I'd like to give you an example here. So an environment that is actually rather uncertain for companies is the used car market. Now, why is this the case? Used cars kind of can differ in many, many different dimensions, basically. And if a dealer kind of gets a car on the lot in the first place, he obviously needs to kind of determine what is the best price. But at any given time, basically, there might only be very few other cars around in order kind of to determine this price. So you have a very, very small reference class, essentially. So how do you actually best price such a car? And just to give you a little kind of story, basically, to start that out. So I was actually shopping some time ago for a used car at the largest BMW dealership worldwide, and what I encountered a car that I very much liked, and I thought, okay, I should be buying this car. But hey, let's have a look around. Maybe I find another car that actually kind of corresponds even closer to my preferences. And indeed, I found another car but which was just identical to the same car, to the first car, but was about 2,000 euros cheaper. So obviously this corresponded more to my preferences, at least kind of in terms of all the objective measures that I had in front of me. But obviously I was kind of very much in doubt, well, maybe kind of this cheaper car is actually, has some kind of quality issues, which I as naive scientist don't really understand in the first place. Therefore I really should be going for the more expensive car, right? Maybe. Right, so this is a market that is really plagued by uncertainty, not just kind of from the perspective of the customer, but also actually from the perspective of the dealer, basically, because also they need to kind of determine what's the best price in terms of selling that car. Now, an important observation that actually Vernon Smith made, and for which he earned the Nobel Prize for a paper in 1952, and they got Nobel Prize in 2002 together with Danny Kahneman, is that you actually can describe markets very well with the rational agent assumption, where the rational agent has all available information. However, at the individual level, the actual individuals or firms operating have very limited information. Now, how can this be actually? I mean, this is a conundrum, right? I mean, you assume in your model perfect information. However, the actual people that you are observing are imperfectly information as such. Now, Smith developed two explanations, one explanation basically, which he kind of labeled as one in constructivist rationality and the other one ecological rationality, what Gigerenzer have been doing previously basically to Smith. So a constructivist rationality is deductive, so it comes from first principles such as a rational agent. It abstracts and completely characterizes an environment. So it moves away from uncertainty and creates an environment of risk where you really have all the alternatives, outcomes, and the probabilities, basically. And then kind of in this risky environment, you can apply optimization. And then kind of via this optimization, you can determine a number of things, such as how the market might look like if more firms enter, how price dispersion basically, or how prices change, etc. So such an optimization calculus does allow you actually to give some very interesting insights, given that a constructivist rationality at the aggregate level, right? Now, an ecological rationality approach is very different from a constructivist rationality. It's inductive, starting really kind of from the bottom up. So really, what does the decision maker actually know in the first place? Then we observe, okay, what is the decision strategy that a decision maker actually has developed over some course of action? So he has had some time to learn, actually. And then this strategy obviously kind of depends on the type of environment that the decision maker is in. And the decision maker tries to select the strategy that seems to make most sense to him, that is, that actually performs best, essentially. And this selection process might or might not yield the same strategy as up here, basically. Actually, very often, given uncertainty, it might yield a very different strategy. That's at least the very hypothesis that we would like to hint at. So what we did here, so in terms of global rationality, we have the used car market. We have the observation that there are two cars which are virtually identical, basically, but differ in price. And what economists refer to that as price dispersion. So in theory, you would assume in a perfectly competitive market with all information that there is no price dispersion, right? If consumers are also perfectly informed and always choose the cheapest product. However, if there are some uninformed consumers, because they don't know the other prices, basically, that there's a cheaper price out there, you actually might get price dispersion in the first place, right? And kind of given such a mix of consumers, the optimal strategy here is to actually use a mixed strategy. This is to randomize between intervals in terms of your price. So kind of have a price today, say 10,000 euros, and tomorrow you have another price between 11,000 and 9,000 euros and kind of pick a price randomly. That's kind of what a constructivist rationality would imply. Now, sorry, call it bounded, it's ecological rationality, sorry, instead of bounded rationality. Now, Simon also looked at a very similar problem to the used car market. He didn't look at the used car market in this 1955 paper, but he looked at the apartment or housing market. And here, what he kind of derived is an aspiration level heuristic. So what he suggested, kind of given that dealers or firms are uncertain about the optimal price, they simply kind of start out with a relative high price, keep the price constant for a fixed duration, say 30 days, and then they reduce the price by a fixed margin, right? So there's no attempt to derive optimal parameters, basically, but a very simple step pricing strategy, basically, that Simon already described in his 1955 paper. Now, kind of the exact duration, for instance, that a car might be kind of be on the market for a certain price, obviously might depend on the specific setting of that of the car dealer. So if you are in Berlin or in Munich, for instance, where there are a lot of customers coming into your shop, you very quickly get a good idea whether kind of you price too highly, therefore kind of the duration might be much shorter than if you're, say, in some rural area in Bavaria, basically very rarely you have a customer that is looking at a specific car, right? So kind of the aspiration level and kind of the specific aspects of the pricing strategy might be well adapted kind of to the specific environment, and that's kind of what Simon's suggesting in 1955, and what we will be looking at specifically in this data set 60 years later, or more than 60 years later, actually. 70 years later. Now, we have three core hypotheses. So due to weak information conditions, so due to limited sample size, dealers actually use the aspiration level heuristic. Now, aspiration level heuristic is well adapted to the specific context. So dealer really kind of select the parameters kind of depending on the environment. So duration depends on the population density, the number of competitors. The more competitors you have, the more easily you can observe what's actually happened, and the quicker you might actually kind of decrease your price. And the aggregate market is well described by a traditional equilibrium model, that is by a constructivist rationality analysis. Right, so what is the data that we have here? So altogether we observe 50 months of data. At Autoscout.de, which is one of two internet platforms for used cars in Germany, where about, I think 90% of used cars that are sold in Germany are actually advertised. We focused on two specific types of cars in order kind of to facilitate the analysis. There was a 320 BMW, which is kind of a middle-of-the-road car, and a 730, which is like a top quality, really expensive car. Now we extracted for all dealers, basically, that for all cars, basically, that we observed during these 50 months, all the 27 attributes on the web page. Then we also had afterwards interviews with dealers, 55 dealers, basically, in order kind of to verify the pricing strategy. Now, what we specifically did, basically, in our analysis here, we looked at twins. So the phenomenon that I was trying to illustrate to you in the beginning. So cars that are exactly identical with all of the observable attributes. This is like the body of the car, for instance. This is like the color of the car. This is what types of tire it has, and all the attributes advertised except for mileage. In terms of mileage, we left a leeway of 5,000 K because obviously you otherwise can't find exactly matching cars, basically. And then for each car, we observed how they are priced over the complete period, kind of from the first occurrence on the market until basically they leave the market, in order kind of to get an idea what is the pricing strategy of a given car dealer. Now, some summary statistics. So altogether, we observed more than 600,000 prices basically for these cars. Obviously, the 320 BMW is 90% of the data set, whereas 730 is about 10% of the data set. And for matching cars, or these twins, at any given day, we have on average 4 cars that exactly match on all of these attributes that are advertised online. And these attributes are central really kind of for determining whether or not somebody buys a car. So it's actually 4 out of 5 customers only visit one dealership in order actually to really buy the car that they initially had identified online as such, right? So these attributes are vital. As I kind of, they're on average 4 cars with exactly the same attributes, and the duration until a car sells is on average something between 30 and 45 days. Now we also have a number of variables that actually characterize the environment, in order kind of to investigate the ecological rationality of the strategy. So on the one hand, we have the number of competitors that dealers face, the population density, so whether you're not living in a rural area, but also GDP per capita, so how much people actually have, how much money they have or can spend basically on their car. Then we have dealership characteristics, and then properties of cars at the dealership, so the average kind of car basically the dealership is selling. Now, just kind of an illustration of the uncertainty that car dealers face here. What you have here is at the last day a car is observed basically, what rank it has in its group of matching cars. So I assume you have 5 cars basically today that have exactly the same attributes. And you can rank these cars in terms of price. So there might be the most expensive car is 12,000 euros, the cheapest car is 9,000 euro. What is the rank of the car that actually kind of disappears today? So is it always the cheapest, which would be kind of rank 5? Rank 1 is kind of the cheapest, rank 5 is the most expensive basically. Right? And what you can see here is that different to the assumption that always the cheapest car is bought. I mean, it is bought in about 25%, or disappears. It's not bought, it just disappears online basically. In 25% of all cases, it is really that the cheapest car disappears from the online platform. But very often it's also a more expensive car. Right? And the same pattern is actually observed for a 730 BMW. So it's not that people, as I would have initially assumed, always go for the cheapest, but that they kind of have some implicit assumption that a higher price also implies higher quality, maybe. But given that we observe all the same attributes, basically, this is not the case. So this is first hint, basically, to the very strategies that dealers are applying here. Now, with regards to supply, there's also a large degree of uncertainty. What you see here for 320 in solid line and 730 is the number of cars available on the platform. And as you can see here, there's large variation. So for instance, in March 2011, when we actually got hold of the data set initially, there were about 4,700 cars advertised, whereas 6 months later, it was only 3,500. So the market is really highly dynamic and unstable, and therefore it's really very difficult kind of to learn from, for instance, when you last sold a certain car, what the best price of the car might be today, right? So you must kind of employ something else than kind of just looking at the past, because the market is just so very dynamic. Yep.
In the previous one, so on the left-hand side graph, what was the difference in the prices at each, like for each rank? Like what was the difference between?
So the average difference, the average price dispersion is about 14% basically between the cheapest and the most expensive car, which is, I mean, if you have that as a profit margin, that's a lot. So. Right, so initially kind of we start with a constructivist analysis, so really from the aggregate market. So can constructivist models describe what we see here sufficiently well, so what you kind of usually would apply in economics? We have some traditional models here, initially kind of started by Varian, but also similar models are then developed by Rosenthal and Bay and Morgan. What we kind of do basically kind of we nest all models in a larger model here in order kind of to determine which of the models really kind of best describes the market. So what you initially have here, that's the kind of price dispersion. So f of p is not the price dispersion, sorry, the distribution of the price, where a price is randomly drawn, and you construct the distribution of the price depending on the number of other cars at a given time. So you might have 5 other cars that are currently identical to the one that you are currently having. Then you have the reservation price of the consumers that you must try to estimate somehow. Then your actual price. And then U and S are the number of uninformed customers, respectively the informed customers. Right, so I mean, I guess kind of I shouldn't go into the details here. So what it is basically, it's simply kind of a formula in order kind of to compute the space from which you kind of draw the price. The rest might not be that important here for the moment. We can talk about it individually maybe afterwards. Now, what's quite important here is really that Lach in 2002 actually did observe that not just at the aggregate level, but also at the individual level, supermarkets use such a mechanism where they have kind of a space from which they draw a price and then kind of advertise their products kind of by this randomly determined price in the first place. So it's not just at the aggregate level, but also can be a good tool at the individual level. But notice that supermarkets live in a very, very different environment, right? I mean, they have lots of data, and the environment is pretty stable. So they actually can parameterize these three equations pretty well, whereas used car dealers do not live in such an environment, right? As I just was trying to illustrate with regards to the fluctuations and uncertainty that they are exposed to. Now, the three models make three very different predictions for the number of matching products or cars on the market that are smaller than 40. So actually, Varian makes a very interesting prediction that price is initially price dispersion. So the difference between, well, a simplified way of saying price dispersion is the difference between the smallest and the largest price, and the average price also increases. So price dispersion, average price increase, whereas Rosenthal says price dispersion increases, average price decreases. And Bain and Morgan kind of say both would be kind of decreasing as the number of competitors actually increase. Now, when you actually look at the market basically and how price dispersion and the price develop in terms of the number of offers, so that is competition here, you might see kind of the first surprise and actually show that the Varian, or deduce that the Varian model is indeed the best model. That is here, as the number of offers increases, price dispersion increases. That is, as more competitors enter basically, the price dispersion kind of increases, indicating also kind of that what dealers do here is some kind of search algorithm, kind of really searching for the best price here in the first place. And then also importantly, the average price actually increases with the number of competitors, right? So something very different than what you would assume kind of in a perfectly competitive market, where you would assume the more competition you have, the lower the price also. So Varian actually kind of provides a very good and accurate description of the market at the aggregate level. Obviously, Varian also implies then kind of that, or all of these three models basically imply that used car dealers should be randomizing their prices. And the question is really, do they do that? And that's kind of the question in the ecological analysis. Now, looking at the three parameters that dealers actually have in order kind of to set their price, it's initial price. So when you get a car first, basically, where do you start out in terms of your price? And there we see that kind of out of, well, the 628 dealers that we observe, only a small margin really of dealers kind of is at the very cheapest end of matching cars. So about 12% of all dealers kind of start out competitively, whereas all other dealers actually have an initial price that is higher than the cheapest price actually in the market, right? So again, hinting at this is not something where competition actually plays an important role, but maybe kind of more the search for the best price. Now, secondly, the price is kept constant. Also here you would assume, I mean, the online market environment is an environment that provides lots and lots of information where dealers can quickly change the price, right? Given kind of all the information theory that they would have. However, what actually dealers do, the price is kept constant. Is not kind of at the lower end, so that would be kind of 5 days or 10 days, but on average, actually, dealer kind of keep the price constant for 30 days. And last but not least, kind of the price change. Also, actually, here you observe that on average, kind of prices decline, actually. So that's 0 here. And the randomization kind of would imply that prices kind of that this whole distribution is actually centered on 0. However, kind of dealers do not randomize, or do not seem to randomize, but actually kind of reduce the price instead of making some kind of like random movements up and down basically with the price. So this kind of is a first hint at actually that something very different is happening in comparison to the randomization that actually the aggregate model would imply in the first place. Yeah?
You know, with the shift in price, does the variance of the distribution overall decrease or increase or stay the same? Like
the variance of the distribution?
Like, for example, the variance of the initial price distribution.
Yeah.
Like, is it the case that the ones who are initially higher than average decrease a bit more than average, and the ones that were initially a bit lower than average decrease a bit less than average, so that in the end the range is smaller than it was originally.
Right. No. What other interviews reveal actually that they have a fixed percentage by which they reduce the price. So, for instance, they might have 10% basically, starting with 10,000, and they go to 9,000, and then they go to 8,100. I mean, that might be an extreme example. Actually, it's not 10%. That would be kind of here, but more like 5% or 2 or 3% basically. But that's kind of what they actually do. Yeah.
So basically, the reason we have things that kind of fly in the face of classical economic theory is because of asymmetry of information. The fact that some customers are informed, some others are uninformed. But I thought that by definition, this is private information to the customer. Still, it shows up in the model as one of the parameters. So I was wondering, how do they actually get that kind of information of the percentage of informed and uninformed customers to parameterize the model?
Yeah. So what you can observe basically is how often really the product is sold for the cheapest price. And that's approximated with the fact that this is kind of the informed customer basically, or the one that really kind of thinks, I have sufficient competence, given the used cars and given it's a complex product, that I really kind of dare to buy the cheapest car in the first place. Yeah, and kind of that then kind of this proxy kind of allows one kind of to derive the share of the informed consumers. Right? Now, kind of the question here is really, how does pricing really look like? So we already have seen kind of, it might not be kind of random price setting as implied by the aggregate models, but something else. So what we have here is the price range among matching cars and the days basically until a car is sold. And what we observe here for more than 50% of all dealers is that they initially start with roughly at the mid of the price range and have 30 days where they keep, is it 30 days? Sorry, 24 days where they keep the price constant. And if the car does not sell, then they reduce the price by a fixed margin, which I just implied, and keep the car again with this price on the market for 24 days. And they repeat that basically until the car sells. And that's precisely what Simon described in 1955. Right? That's what half of the dealers do. Now, the other half does something similar, basically, but with some variations in the parameterization of their strategy. One uses much longer duration, basically, and then has a larger percentage change, basically, by which the price is reduced. And then kind of keeps the price again constant for like, I think it's 45 days and then 37 days or something. But they have like these fixed periods basically where they kind of keep the price constant, and if the car doesn't sell again, they kind of reduce the price. And then there's some dealers, these are particularly kind of small dealers that just have a flat price and constant and kind of wait until they sell basically. So this is precisely, I think, kind of very strong evidence for what Simon postulated in 1955, given an uncertain environment, given an uncertain market. You have such aspiration level pricing, and not a randomization between, from a distribution basically as applied by the aggregate models that actually do describe the aggregate market rather well. Now, as I hinted beforehand, we were also talking to the dealers in order kind of to verify these results, and I think kind of this nicely confirms our observations also online, basically, how they set prices. So if you just look at the initial price, and down here are then the numbers, 72% of the dealers basically say that they are pricing higher than their competitors actually initially. And with regards to duration and price change, a fixed duration and a predetermined amount by which kind of the prices changes is also applied by 26% of dealers even, right? So they really kind of have to ignore all of the, like they can just set the car out there and then have like a fixed regime basically by which they change their prices. They just totally ignore what's happening in the market. Right. And obviously kind of why prices might be kept constant. There are a number of theories in economics basically. So what we also use these interviews for, we presented these theories in simple terms and asked whether any of these theories can explain why prices are kept constant. Is it really kind of aspiration adaptation, so the search for the best price? Or here, another theory is that dealers price in terms of price points, so psychologically attractive price points. So some consumers particularly buy more often if the price ends in 99 or 10,900 basically. So you only jump from 10,900 to 9,900 basically, which is an important driver of pricing and has been suggested in the literature. So price points and aspiration level are both elements that dealers strongly agree basically. So the scale altogether goes from 1 to 4, whether or not they agree with a strategy, whether it applies basically to the pricing, and all other kind of conventional strategies that refer to kind of some transaction costs, for instance, just do not explain why dealers set their prices. So it's really search for the best price and really addressing kind of consumer in order kind of to extract the most profit in the first place. And last but not least, some regressions again in terms of the ecological rationality of these price setting regimes. So we have again our three components for pricing strategy: the initial price, the duration, the price is kept constant, and the price change basically. And what you can see here is the number of dealers in a region. So that's the comparative pressure. But also kind of that you actually might be able to observe other dealers and what they do. And that actually kind of yields to not that it affects the initial price as conventionally assumed in economic theories, that kind of as competition increases, you kind of might lower the price. This is not the case. But rather kind of you lower the time that you observe whether a car sells for this price essentially, right? And it's also not price change, just doesn't affect anything at all. Similar, if you look at population density, so the number of consumers, the demand side, it's not the initial price that is affected here, but rather kind of the more densely populated an area is, the shorter is the duration that you actually have, that you kind of keep the price constant. GDP per capita, same thing basically up here. So the richer an area is, the more constant, the longer constant you keep the price, because you might think, okay, it might be worthwhile to wait a little longer because somebody is living in around here that really kind of buys. And then the interaction effect of dealers times population density is also positive. So implying a strong effect of really kind of searching for the best price. And it's not competition that drives this market. Now, final questions that we asked here is, what if? We actually would kind of tell dealers, hey, you shouldn't be using the aspiration level strategy. This is nonsense. This is not optimal, whatever that means, but you rather should be using a random mechanism basically to set the prices. So what we did here, we have, so Varian provides an equation basically in order to kind of derive the profit margin. The profit margin can be also determined, or a rough proxy of the profit margin can be also determined from the aspiration level pricing. For the constant duration, the decreasing duration, and the constant price. So the three strategies that we just saw beforehand. And that's the roughly kind of gross margin 2 level that we can actually estimate in terms of profits that dealers make. And that's the mixed strategy in terms of the margin that dealers would obtain if they would have priced differently. So strongly suggests that dealers are well adapted to the uncertain context that they are pricing in basically, and that they're doing something pretty sensible in the first place. Now, to quickly wrap up, what I was showing to you here is that a constructivist rationality analysis really does make sense, also in an uncertain context, but only if you take on an aggregate level perspective. However, kind of the assumptions that you base your model on, the rational agent basically, and how it operates, that's useful for your model, but it might not be useful at all how the individual should be operating out there. Rather, the individual, if it has sufficient experience, like the car dealers, might really have developed something that sufficiently works well actually kind of and leads them to somewhere that is actually sensible for them. But what it implies is really that a constructivist and ecological rationality are complementary analysis. They're not enemies, competitors in this case really, but there are two different perspectives to look onto a problem in the first place, given an uncertain environment for the individual. Now, just to conclude, what we have seen here, many environments are characterized by limited information. Now, satisficing yields are large benefits than optimization, or can yield, not always the case. You really should be doing careful analysis. And simple strategies can outperform complex strategies. I think we've shown nicely in two cases. But also that don't kind of dismiss constructivist rationality altogether in an uncertain environment. Constructivist rationality does make sense, but really at the aggregate level, how the individual then acts might be something entirely different. Thank you very much for your attention, and I'm looking forward to the questions.